Technical stewardship is what separates a project that merely produces drawings from a project that delivers a safe, operable, maintainable, and sustainable asset. You can have an experienced engineering team, an aggressive schedule, sophisticated software, and a strong client relationship, yet still lose technical control. Why? Because technical quality does not protect itself. It requires an independent structure that continuously asks whether the engineering is complete, whether the risks are understood, whether the right people are making the right decisions, and whether the asset will perform safely throughout its life cycle. That structure is technical stewardship. Technical stewardship is not another layer of checking. It is not a ceremonial audit performed before a major milestone. It is not an administrative burden imposed on project engineers. It is a risk-based engineering governance system that connects project execution with the wider technical authority of the organization. On-project engineers are focused on delivery. They manage interfaces, documents, changes, client comments, vendors, budgets, and schedules. Off-project discipline authorities carry a different responsibility. They preserve technical standards, organizational knowledge, engineering consistency, and professional independence. Technical stewardship creates the formal link between these two groups. Without that link, projects can become technically isolated. The project team begins solving problems only within the boundaries of its immediate experience. Decisions become driven by milestone pressure. Deviations become normalized. Incomplete information is accepted because the schedule demands progress. Technical compromises accumulate quietly until they appear during construction, commissioning, or operation. The purpose of stewardship is to identify that drift before it becomes failure. Every engineering location should therefore establish a technical stewardship plan. This plan defines how the engineering management team will govern technical work, scale assurance according to project risk, and protect engineering integrity across the asset lifecycle. A useful stewardship plan does not simply list procedures. It defines the strategy, organization, systems, responsibilities, competency requirements, technical reviews, approval gates, and improvement mechanisms that will control engineering risk. The plan should also distinguish between minimum mandatory assurance and project-specific assurance. Minimum controls create consistency, but no standard plan can anticipate every execution risk. Project management and engineering management must remain alert to risks created by unusual technology, inexperienced teams, complex interfaces, weak client organizations, compressed schedules, difficult contractual conditions, or unfamiliar execution locations. When those risks exist, additional reviews must be planned and recorded in the project execution plan. This is an important distinction. Technical stewardship must be risk-based, not mechanically checklist-based. A small, familiar project executed by an experienced team may require a relatively light stewardship model. A technically complex project involving new technology, multiple offices, inexperienced personnel, and severe schedule pressure requires much deeper intervention. Project value alone cannot determine the level of stewardship. A low-value modification can create a major process safety risk. A small control system change can disable a protective function. A minor piping modification can introduce vibration, thermal stress, or an inaccessible maintenance arrangement. A limited electrical change can affect protection coordination or hazardous area compliance. Risk is shaped by complexity, consequence, novelty, interfaces, and organizational capability, not only by cost. One principle must remain non-negotiable. Schedule pressure must never influence the assessment of technical quality. You may decide to change the execution strategy because of schedule constraints. You may add resources, resequence activities, or revise delivery priorities, but you cannot redefine an incomplete design as technically acceptable merely because a milestone is approaching. When a stewardship review identifies incomplete calculations, unresolved interfaces, weak verification, incorrect design assumptions, or insufficient safety evaluation, that condition must be reported clearly. The response must be corrective action, not technical rationalization. Stewardship must therefore retain independence from the project delivery pressure it is intended to challenge. The location engineering management team normally carries this responsibility. It is typically led by the location manager of engineering and supported by the most senior representatives of each engineering discipline. Reviews may also be performed by nominated specialists who are not directly associated with the project. That independence matters. A reviewer who is embedded in the same delivery pressures as the project team may unconsciously accept the same assumptions. An independent discipline authority can ask a more difficult question. Is this design truly adequate, or has the team simply become comfortable with its own decisions? When significant issues are discovered, they must be communicated in writing to project management, engineering management, or operational management. Written communication creates visibility, ownership, and traceability. It prevents critical observations from disappearing into informal conversations. The process should not stop at issuing findings. Remedial actions must be agreed, assigned, tracked, and verified to closure. This is where many assurance systems fail. They generate observations but do not create resolution. A review report may look impressive, yet the same technical exposure remains because no one owns the corrective action. Effective stewardship closes the loop. The corporate engineering leadership establishes the wider governance framework. It ensures that suitable regional engineering structures exist, mandatory engineering requirements are defined, management system documentation is available, and deviations from mandatory requirements are formally controlled. Regional engineering leadership ensures that offices have appropriate engineering structures, prepare local stewardship plans, comply with those plans, support reviews, and contribute to continual improvement. Where a regional role does not exist, those responsibilities must revert to the appropriate corporate or engineering authority. Responsibility cannot disappear merely because an organizational position is absent. At the location level, the manager of engineering carries the central stewardship obligation. This role must ensure that the technical stewardship plan is prepared, implemented, maintained, and understood. The location must have an appropriate engineering organization, clear project structures, documented responsibilities, suitable engineering systems, and competent personnel. The manager must approve engineering review schedules, examine review results, agree corrective actions with project leadership, and ensure those actions are completed. The role also requires monitoring project performance across quality, schedule, and budget. However, this monitoring is not intended to trade one parameter against another. Poor schedule performance may trigger an additional review because schedule stress often increases technical risk, but schedule urgency cannot be used to reduce the required technical standard. The manager of engineering must also ensure that review effort is included in proposals and project budgets. This may appear obvious, but it is frequently neglected. Organizations demand independent technical assurance without allocating hours for reviewers, discipline authorities, or specialists. The result is predictable. Reviews become rushed, delayed, or superficial. Technical stewardship must be planned as real work. It requires competent people, defined scope, scheduled time, and funded effort. The first major element of the stewardship plan is the engineering management system. All engineering work should be executed using the approved organizational processes, procedures, standards, templates, and control documents applicable to the location and project. Project-specific adjustments may be necessary, but deviations should be minimized and formally approved. The objective is not procedural rigidity. The objective is controlled consistency. When each project invents its own engineering methods, document controls, verification routes, and approval practices, technical performance becomes dependent on individual habits. Organizational learning is lost. Accountability becomes unclear. Interfaces weaken. A common engineering management system gives every participant a defined operating framework. Within that framework, disciplined task and deliverable plans are particularly important. These plans establish who prepares, checks, verifies, and authorizes each engineering deliverable. They connect project activities to the applicable procedures and technical standards. This eliminates one of the most dangerous statements in engineering. I assumed someone else was checking it. For every critical deliverable, preparation, verification, and approval responsibilities must be explicit. The second element is organization. Every office and every project needs an engineering structure proportionate to the work. Titles alone are not enough. Reporting lines, authority boundaries, interfaces, and escalation paths must be understood. Larger projects normally require a dedicated project engineering manager who coordinates the multidisciplinary engineering function. Disciplined chief engineers protect technical standards and provide independent authority. Lead engineers manage discipline execution. Technical specialists provide deeper expertise in areas where normal discipline capability may not be sufficient. These roles are different and should not be blurred. The project engineering manager integrates delivery. The lead engineer controls discipline execution. The chief engineer protects discipline integrity. The specialist resolves advanced technical challenges. When one person informally performs all four roles, independence disappears and workload concentration creates risk. The third element is clearly defined responsibility. The stewardship plan should identify the obligations of the location engineering manager, project engineering manager, discipline chief engineers, lead discipline engineers, and technical specialists. For each role, the organization should define decision authority, review responsibility, escalation requirements, approval limits, and interface obligations. Ambiguous responsibility creates silent gaps. Everyone participates, but no one is accountable. The fourth element is competency. A technically correct process cannot compensate for an incompetent person occupying a critical role. Every technical position, whether project-based or non-project-based, must have defined competency requirements. Competency is more than academic qualification or years of experience. It includes relevant technical knowledge, practical application, familiarity with applicable standards, understanding of project complexity, judgment under uncertainty, and awareness of the consequences of technical decisions. A highly experienced engineer in one sector may not automatically be competent to approve work involving unfamiliar technology or risk. The manager of engineering must therefore ensure that people are matched to roles based on demonstrated capability, not only availability. Where competency gaps exist, the response may include supervision, specialist support, restricted authority, additional verification, or targeted development. Ignoring the gap is not an acceptable strategy. The fifth element is safe and sustainable engineering across the asset lifecycle. Engineering must deliver more than a facility that can be constructed. It must protect technical integrity, integrate safety into design, and support sustainable lifecycle performance. Technical integrity means that systems, structures, and equipment are designed to perform their required functions under defined operating and environmental conditions. Safety in design means that hazards are eliminated or reduced through engineering decisions before they are transferred to construction personnel, operators, or maintainers. Sustainable design means that lifecycle impacts, energy use, resource consumption, maintainability, emissions, waste, and long-term asset performance are considered during design, not treated as late-stage additions. These three dimensions must be integrated into the project execution plan and translated into specific activities, responsibilities, and deliverables. The sixth element is technical peer review. Structured reviews at approximately 20, 60, and 90% design maturity provide three different forms of protection. The early review tests whether the design basis is sound. At this stage, you challenge assumptions, technology selection, applicable standards, process configuration, safety philosophy, design criteria, and major interfaces. The purpose is to prevent the project from developing the wrong solution efficiently. The middle stage review tests whether the design is converging correctly. You examine multidisciplinary coordination, equipment definition, layout development, calculations, control philosophies, operability, maintainability, safety actions, and vendor integration. The late review tests readiness for final issue. You look for unresolved comments, missing information, incomplete verification, inconsistent documents, construction risks, and residual technical gaps. These reviews must not become progress presentations. A review that only confirms what the project team has completed adds little value. A technical peer review must challenge the design. It should ask what assumptions remain unverified, what could fail, where interfaces are weak, whether operational experience has been incorporated, and whether the current maturity genuinely supports the next project stage. The seventh element is gatekeeping. Gatekeeping creates formal decision points before documents or engineering packages move to the next status. Typical gates may control the issue of design information for detailed design, construction, or procurement. A gate is not merely a date on the schedule. It is a readiness decision. Before passing the gate, the project should demonstrate that defined technical criteria have been satisfied. Deliverables must have the required maturity. Verification must be complete. Critical comments must be resolved or formally managed. Interfaces must be understood. Required approvals must exist. When a project passes a gate without meeting these conditions, the organization is not accelerating delivery. It is transferring uncertainty downstream, where correction becomes more expensive and disruptive. The eighth element is continual improvement. Lessons learned should not be a final workshop where participants record generic statements and then return to old habits. A useful learning system captures specific technical failures, successful practices, recurring review findings, interface problems, and corrective actions. Those lessons must then influence future procedures, checklists, proposals, competency development, and project execution plans. Stewardship is not complete until experience changes future behavior. Certain requirements should remain mandatory in every location plan. An appropriate engineering organization, defined stewardship responsibilities, task and deliverable planning, lifecycle safety and sustainability provisions, staged technical peer reviews, and an active lessons learned process. Any departure from the established stewardship framework must be formally approved by the appropriate engineering authority. This is essential because uncontrolled deviation is one of the fastest ways to weaken technical governance. Exceptions may occasionally be justified, but they must be visible, reasoned, and authorized. Here is the practical message. Technical stewardship is not there to police engineers. It is there to protect engineering from isolation, assumption, inconsistency, competence gaps, and delivery pressure. It gives the project team access to wider organizational knowledge. It gives engineering leadership visibility of emerging risk. It gives management a disciplined basis for deciding whether the project is technically ready to proceed. Most importantly, it protects the people who will construct, operate, maintain, and live with the consequences of the design. You should never measure stewardship by the number of reviews completed. Measure it by the quality of decisions improved, risks exposed, actions closed, and failures prevented. A mature engineering organization does not wait for a serious incident to discover whether its technical governance works. It establishes the systems, authority, independence, competency, and review discipline before the pressure arrives. Because when project conditions become difficult, people do not suddenly rise to the level of written intentions. They fall back on the strength of the systems, roles, and technical culture already in place. That is the real purpose of technical stewardship: to keep engineering safe, disciplined, and accountable when cost, complexity, and schedule are pushing in the opposite direction. A file site turn file 0